Well, thank you very much. All right, so let's go ahead and get started. So to kick us off, we have a hybrid presentation today. I am the half that is here in person. My name is Nicholas Boucher, and Russ. All right.
Hi, I'm Ross Anderson. I'm Professor of Security Engineering at Cambridge and also at Edinburgh. Can you hear me loud and clear?
Yes, indeed.
Okay, over to you, Nicholas, for the first part of the talk.
All right, thank you, Ross. So today we are here to talk about Trojan source and bad characters, invisible hacks, and reluctant patching. So welcome to our hybrid talk. You think that the world is a beautiful place. The sun is shining, the trees are growing, the flowers are blossoming, the children are playing, and your source code does exactly what you think it does. So I'm here to tell you that you are wrong. It is raining, the trees are being cut down, the bees are missing, the children are all on TikTok, and oh yeah, your source code may contain malware that you can't see. So meet Jerry. He's a nice guy. He plays tennis, he likes ice cream, he's the favorite child of his family, he's a part-time doomsday prepper, and he also happens to be a very talented developer who maintains some open source projects on GitHub. What Jerry doesn't know is that he's about to cause the largest cybersecurity incident of the year. Why? Because Jerry's human. He's not a robot, he's not a billionaire, he's not a billionaire robot. He's just Jerry, and he's vulnerable to attacks that he can't detect. So let's talk about invisible attacks. Humans communicate in lots of ways. There's verbal communication, there's sign language, there's smoke signals, and then there's writing. In fact, one or two people in this audience may actually be old enough to remember a bygone era where people used this primitive tool. I am told it was called a pen to write things down with these little hand gestures. And apparently they actually wrote things on dead trees, which they presumably cut down in some sort of a way to assert their dominance over nature. History is a pretty crazy place. And then we get to the more civilized era where we have these things called computers. And at this point, someone had to figure out how to represent good old-fashioned writing in a digital format. And not everyone agreed on how this should be done. So one of the more popular methods of encoding text was known as Ascii, but it could only capture Latin characters. And of course, there's no issues with that, right? I mean, I'm sure the whole of human language can be represented in basic Latin characters. Okay, so maybe not. I asked around, did some polling, and it turns out that people do speak languages other than English. And this meant that lots of different text encoding standards developed in parallel. And if you've ever opened a file using the wrong text encoding, you know that it always produces some kind of dark magic spell that seems to summon Cthulhu from the depths of the Mariana Trench to wreak havoc across your computer screen. So let's talk about Unicode. To fight off this evil, the world's greatest scientists came together and created a single unified text specification that aims to be capable of representing all of the world's languages. It's called Unicode. And these days, almost all digital text is represented using this specification. Pretty much everything from email to Twitter to angry YouTube comments to source code is all just Unicode under the hood. Now, here's an interesting feature of human writing. Our species doesn't seem to agree on the direction that text should be written. Now, if you're a writer of English or German, you probably write in left to right direction. But if you're a writer of Hebrew or Arabic, you probably write in right to left direction. And since Unicode aims to represent all of the world's languages, this means that it must have some way of capturing both directions of writing. It also means that it must have a deterministic mechanism to combine text with differing directionalities. So for Unicode, this is called the Bi-Directional Algorithm, and it's about to become your worst enemy. So let's take a tour of the Bi-Directional Algorithm. Each character has a natural directionality associated with it. This allows English to default to left to right, while Arabic can default to right to left. And when text of differing directionalities is mixed, characters are combined to some sensible default. Sometimes this default might not be what you want. And to support this, a set of directionality control characters were created. And this allows very fine-grained control over text directionality. So let's consider an example. We start with the text A, B, C, which naturally displays as left to right. And then we add control characters, which override the directionality to right to left, and then resets back after the text. So now the text will read as CBA, despite the underlying logically encoded order still being A, B, C. So things get a little bit more complicated when we realize that directionality control characters can be nested within each other. So welcome to the multiverse of madness. Here's another example. This time we have the text A, B, C, D, E, F. We place two separate left to right control sequences around ABC and DEF respectively, except that now we wrap this entire sequence in a right to left environment. So what happens now? The text displays as DEF ABC. And to make this a little bit more apparent, let's put some boxes around the different segments of text that are on the screen to make it a little bit more clear. Now, you see, the ability to nest directionality control characters allows very fine-grained control over character display order, despite the logically encoded order of the text that's sitting on the disk. So what could go wrong? This seems fine. All I've shown is that we can create deterministic complex differences between the logically encoded and visually displayed orders of text. So at this time, please fasten your seatbelts, raise your tray tables to the upright and locked position, and anticipate the cacophony of crying babies as we begin our descent down into the rabbit hole. So remember all of those references to source code a few minutes ago? Since most source code is written in Unicode these days, it means that source code supports all of these nifty bidirectional features. Cool, except wait a minute. For source code to do anything interesting, it needs to be run through some sort of compiler. But the thing is, those compilers, they don't care about the display order of text. They ingest the raw bytes of source code, and this means that they process the logically encoded order of text. So where could we be going with this? So Dr. Evil over here has been thinking, and he thinks that he can use this stuff for some nefarious purposes. What if he were able to inject some of these directionality control characters into source code such that the code appeared differently to humans and to compilers? He's sure he could find a way to do something evil with that, but how is he supposed to inject those control characters arbitrarily into source code? Surely those characters would break the syntax of the language and cause some kind of compiler error. So it seems like we're saved. But Dr. Evil thinks about it some more, and he realizes that virtually all programming languages will let you put arbitrary anywhere into source code. You may have heard of this feature before. It's called a comment. And I'm sure that everyone here is familiar with comments in code because everyone in this audience definitely takes the time to document every line of code they write. And it turns out there's actually another way that you can inject arbitrary Unicode into your source, and that is string literals. In most languages, you can put just about anything between double quotes, like our good friend Dr. Evil is demonstrating for us here. So let's recap. Humans can't agree which direction text should be written. So we designed computers that support both left to right and right to left text. We implement this in a specification called Unicode, which gives us special control characters that allow fine-grained control over the display order of text. And it turns out that compilers ignore the display order of text in that we can smuggle these directionality control characters into source code by placing them in comments and strings. Great. So what's the problem? Well, here's the thing. Dr. Evil is a pretty clever guy, and he realizes that he can use directionality control characters in comments and strings to visually reorder source code tokens to present different semantically correct logic to humans and to compilers. So that's a really big deal. So let's state that again. Semantically valid control characters in comments and strings can visually reorder the surrounding text to look like syntactically valid source code that's not actually there. So this means that you can encode source code so that it looks like it says one thing to humans, but actually says something different to compilers. So let's look at an example. And since we are about to talk about an attack, let's officially switch the presentation to dark mode to let the world know that we are indeed real hackers. So consider the following program in C. Its behavior appears pretty straightforward. It begins by setting the Boolean variable isAdmin to false. It then checks whether that same variable is true, and if it is, it prints out that you are an admin. So we would therefore expect that this program would have no output, but let's run it and see. Okay, so that's strange. It seems to say that we are an admin. So let's take a look at the underlying encoding, which I visualized on this screen to help explain what's going on. So the line of code with the if statement has actually been reordered using directionality override characters. Let's zoom in on that line. And it's a bit tough to see what's going on here. So let's look at this animation that alternates between what a human sees and what a compiler sees. So, and now the issue starts to become clearer. If a human sees an if statement, the compiler here is just seeing a comment. And this is a toy example, but you could imagine that this if statement is gating something far more substantial. Like imagine administrative control over a power grid or something like this. So we found a way to encode source code such that it looks innocuous to humans, but does something pretty evil in the eyes of the compiler. And it turns out that there's lots of ways that this can be explained. Using directionality control characters, we're effectively anagramming adversarial program A onto a benign-looking program B. So we call this the Trojan source attack. And by the way, if you weren't already angry at the world by this point, let me call to your attention that Trojan source attacks persist through copy and paste. So that means that if someone posts a code example on a forum that contains an invisible attack at the encoding level, that attack will still be there when you paste it into your code base. Great. So back to Jerry. He has been busy cleaning out his doomsday shelter for the past few minutes. You know, when he's not busy preparing for the end of days, Jerry maintains a project on GitHub. And it's something pretty boring. Let's just say that it's an XML parsing library. And it so happens to be the most popular XML parsing library in the ecosystem, because that is how the internet works. So perhaps some of you have seen this very informative infographic in the past, which describes how bulletproof our modern software supply chain is. Well, we are about to get into that. So one random Tuesday morning, Dr. Evil makes a pull request against Jerry's GitHub repo. It includes what appears to be some optimizations to code that will just make it run better. Jerry takes a look through this and he's happy to merge it into the main branch, right? It makes sense, it's good looking code. So the change is automatically pushed out to a whole bunch of different package managers. And over the coming days, all downstream projects that use this library update to use the latest version. Great. And before you know it, this source code is deployed in some online widgets, a couple of e-commerce sites, maybe a major operating system or two, and perhaps the crucial infrastructure that powers the electrical grid that's powering ventilators at a hospital. Fantastic. So if you haven't guessed, Dr. Evil had used the Trojan source code to encode an invisible vulnerability into the code that was merged into Jerry's open source XML parsing library. And let's say that it introduced some behavior that upon seeing XML of a certain format caused it to just execute what was ever contained inside that XML. So why is this terrible? Well, Dr. Evil can now use this to remotely take over any machines running code that consumes Jerry's XML parsing library. And the best part about this is that any human that is looking at the open source code that this project is running on won't see anything unusual, because the vulnerability is hidden in the text encoding rather than being overtly visible in the traditional fashion that we would expect from source code that we find online. So that's the Trojan source vulnerability. But are there any other ways that we could use Unicode tricks to wreak havoc on the world? Well, surprise, the answer is yes. So let's talk about machine learning. It's the future of code, right? Next generation software systems will contain increasing reliability on machine learning models that perform increasingly complicated tasks. And unlike source code, machine learning models are represented by numerical weights assigned to nodes in a complex network that we like to post pictures of onto the internet when we want people to think that we're smart. So for everyone else, you've realized that you've been living in the matrix this entire time. You suspect that nothing has meaning, and you are bracing yourself to see which other mission-critical systems are about to fall apart. Cool. So if you're the sort of person that's interested in machine learning, you've probably seen this picture before. If not, what you see on the left is an image of a panda. And when we put that image through a machine learning model that's supposed to do some computer vision and tell us what's in the image, we see that the model tells us we are looking at a panda. Great. But then we add a tiny amount of invisible noise to the picture, and all of a sudden, the model thinks that we're looking at a gibbon. This is the classical case of adversarial examples in machine learning. But adversarial examples at their core are just inputs to models that look normal to humans, but can make machine learning models output incorrect results. So this particular example seems mostly harmless, unless, of course, you happen to be a cuddly panda living in a world full of killer robots programmed to attack gibbons. If that is the case, your life definitely sucks. But I promise that things are about to get much worse than this. So traditionally, adversarial examples have been focused on images. And this makes sense. It's actually quite easy to make subtle changes to pixel values in images that are just too small to be easily detected by humans. But things become much harder talking about text. Researchers have tried to generate adversarial examples in the text domain, but the issue is that text is just more discrete than images. It's hard to make small changes to text. Any change that you make is likely going to be variable to humans that are looking at this text. And techniques that researchers have tried in the past to make perturbations to text include misspelling words or changing the order of sentences, paraphrasing and things like this. But the challenge is that these are just less compelling techniques than the image-based techniques because they make visible changes that are going to be detected by humans. So here's where we get back to our Unicode tricks. Earlier, we decided that we could change the directionality of text such that the logical and the visual order of characters were different, effectively reordering the characters on the screen. Now, in the Trojan source attack, we started with a desired logical ordering and modified the visual ordering to suit our purposes. So let's do the exact opposite of that. Let's start with a fixed display order for characters and then modify the underlying logically encoded order to suit our needs. So recall from the example earlier that we discussed where we had a logically encoded string ABC and naturally it displays as ABC without any changes to it. Now let's do the same that we did before, but let's reverse the characters in the logical encoding to exactly offset changes in the display order. So this means that the text is encoded as CBA, but it still displays as ABC. So what's the issue here? So we've just demonstrated that we can make invisible changes to text. And guess what? Machine learning models get extremely confused in the presence of text that is reordered at the encoding level. So why would anyone want to do this? Well, let's go back to our good friend, Dr. Evil, who I presume is currently sitting in prison for his Trojan source attacks that he launched against the XML parser supply chain. So these days, Dr. Evil spends most of his time on social media, and he's pretty angry at the world, and he often tries to post some pretty nasty stuff online, hate speech, disinformation, calls to violence, all of that kind of stuff. But fortunately, lots of places on the internet have hate speech detection that attempts to block things that are either highly inappropriate or might be intended to incite violence. So the news is almost all of these toxic content detection systems are powered by machine learning. And it turns out that Dr. Evil, all he has to do is encode his hate speech using some logical reorderings, and he'll be able to get past the undefended toxic content detection models virtually 100% of the time. So social media, video comments, blog posts, Dr. Evil, and any other person who has come across this research can now just evade toxic content detection. And it turns out that logically reordering text directional control characters is just one of multiple ways to break machine learning models. You can also inject invisible characters into text, which will have no effect on the rendering of that text, but does indeed change the underlying encoding. Or if you'd prefer, you can swap out characters with homoglyphs, which are characters that look the same, but have different encoded representations. And if you don't like that, you can actually just inject arbitrary text into your strings and then inject some backspace control characters following that text so that it's removed before. Cool. So the bottom line is that there's lots of ways to use Unicode to logical encoding of text without affecting the way that the text looks. And using these uncommon encoded representations typically causes machine learning models to fail. And the best part about these techniques is that they generalize to virtually all natural language processing systems. Machine translation, textual entailment, toxic content detection, named entity recognition, sentiment analysis. These are just a few of the systems that we're able to craft real examples against. And to make this a little bit more clear, let's look at one particular example. Let's say that we had a machine translation model, and perhaps it's the sort of thing that for some crazy reason we run invoices through so that we can read them in our native language. And let's say that in this case, we're inputting English and we are outputting French. By just putting in a single reordering control character, we can change the underlying logically encoded order of the account number in this theoretical example, such that when the French is spit out the other side of the model, guess what? It's going to take that logically encoded number, and all of a sudden, we are saying that we're going to send money to a different account than was on the invoice that we sent to this customer. So to put this in one precise way, Unicode breaks machine learning. So with all of that, let me pass the torch over to Ross, who's going to the portion of this presentation. Ross, I will put you up on the screen.
Thank you, Nicola.
Wow. Oh boy. Sorry, Ross, give me one while we deal with the well, yes. Why is that happening? That's why that's happening. Let's do this. That's
right.
better.
Can you see the next slide?
Yes, Ross, you are up. We can see you and can see your slides.
And can you see the slide after that, coordinated disclosure? No? Yes or no?
Yes, you can.
Okay, because it says you're sharing another application window. I take it I'm just to ignore that and carry on. Okay, if something breaks, then let me know and we can fall back to plan B, where you'll drive these slides and I will do the talking through this wonderful internet thing. So here we have a class of attacks which can break software in just about any programming language that you're likely to use. Anything between Fortran 4 and Haskell will typically have Unicode support, and that means that it can be attacked using these mechanisms unless you can somehow block them, whether in the language or in the development environment or somewhere else by means of tools. So when we discover something like that, the ethical thing to do, of course, is coordinated disclosure. And in this case, that proceeded in two phases. We disclosed the bad characters attacks first, because they're the attacks that we discovered first. And then when we realized that they worked for source code as well, we did a separate round of coordinated disclosure for Trojan source. Can you see the next slide?
Yes.
Okay, so one of the things that you learn through an exercise like this is who cares. Now, talking first about the Trojan source disclosures, there's a number of ways in which you can do this. Now, the long-term fix will probably involve changes to the Unicode spec, and Nicholas will be happy to talk about that in the questions afterwards or over a pint or whatever. That is work in progress, and it is depressingly slow, as you would imagine with a standards body. Another thing you can do is fix it in the language. You can simply change the language spec so that it will not accept anywhere an unterminated BD command, whether in string literals or in comments. Another thing you can do is fix it in the editor. And this is interesting because it means that organizations have got a chance to blame somebody else. And this basically enables you to learn fairly quickly who actually cares about stuff. And to give you an example of two extremes, when we did our first responsible disclosure, the people who were so eager they almost bit our hand off, or the Rust team, they were extremely eager to fix the language spec and to roll it out just as quickly as the responsible disclosure period would allow. And they also let us look through vast repositories of online codes to check that the attack had not yet been carried out. At the other extreme, Java, which was the latest, greatest thing as Rust is now, only back in the mid-1990s, is now sort of maintained by Oracle, which treats it as a source of rental income. And the Oracle team fairly quickly said that this isn't our problem, this isn't a bug in Java, it's a problem for the editor that you happen to be using. And in between those two extremes, there was a fairly wide range, and various companies acted as you would expect these companies to behave. Amazon is not really part of the ecosystem. Apple's extraordinarily secretive, and they acknowledged the disclosure but didn't say anything about what they would do or when. Various other firms either couldn't accept a bug report because their bug reporting website was broken, or in the case of another large firm, they said, we're not saying you're a bug bounty because we know about this bug already. And we said, well, in that case, what about the following two languages that you maintain? And they said, oops, and eventually backtracked. And so the process of getting a vulnerability disclosure acknowledged and acted on is often a long and complex process. And we found that in practice, it took publicity plus contacts plus patience. Now, in the case of our Trojan source vulnerability, sorry, were you saying something? Okay. In the case of the Trojan...
No, I think we had some network lag there.
Okay. In the case of the Trojan source vulnerability, of course, the issue here is largely about supply chain attacks. I can recall a few years ago, we discovered an attempt to introduce a vulnerability into WebKit. And that is, of course, used by the browsers in iPhones, Androids, and elsewhere. And if this vulnerability had managed to be smuggled in, then the person who had done that might have been able to sell that vulnerability for millions of dollars to one of the cyber arms vendors. And this is the case that you're particularly worried about. Somebody might have used this to sneak something in that they then sold and which is being exploited on a zero-day basis. And but it's not the sort of thing which in itself gives a 0 day. It's not something that you can take to a cyber arms manufacturer and say, here is a 0-click remote exploit of BIOS. The other thing about this particular vulnerability is that it's a new kind of vulnerability. Now, a significant number of the 19 firms to which we disclosed used contractors to deal with their bug bounty programs. HackerOne was the most common, but there were a couple of others. And the response from these 10 firms was to dismiss the problem. And that meant that we had to take the trouble to go and contact the software maintainer that was their customer, and then explain what was going on, and then eventually perhaps say to the factor that yes, this is a vulnerability for something is to be fixed. We then discussed with people in the client firms, and they said, well, the difficulty here is how do you go about writing a scope for your contractor? And so you write scopes which explicitly deal with things like 0-click remote exploits of your operating system. And anything that looks a bit weird or odd or academic, you can't really do that. And so the natural response, the first responder will be to brush it off. And we find that with other vulnerabilities, and we find those sins. So the first thing that we learn is that unique vulnerabilities are difficult if it's not something that falls into the well-known categories of SQL insertion or cross-site scripting or After-Free or whatever. Anything that requires explanation and for which you don't have a nice proof of concept, then you're going to struggle. The second thing that we discovered is that it makes a big difference once you've got a CVE number. Now, how that system works is that each software vendor is its own authority for issuing CVEs on its own system. And we couldn't get Unicode to issue a CVE on theirs because they didn't initially acknowledge that there was anything wrong. However, there is a CVE issuer of last resort, MITRE, and it's not about to be trivial to get them to give us a CVE number. In fact, we got two. And once we had those, and that opened all sorts of doors, all of a sudden, the first responders started taking those Trojan seriously. The third thing that we discovered is that once you're within the CERT, the CERT can really, really help. And the reason for this is that they've got various back-end infrastructure which enable people to set up discussion groups for all the various firms who are involved in coordinating disclosure. And once you can get the firms to whom you're doing this disclosure working together on the same discussion group, they can collaborate with each other, and they can encourage each other and swap ideas and give each other support. So this is something of which we were completely unaware until we went through the process for ourselves. And the final thing that I would like to highlight here is your friend. And the reason for this is that there are a number of development teams, such as GCC, which do not have a mechanism for you to do some kind of responsible disclosure on the basis of 90-day embargo. Because everything that happens in GCC is open, that was the stolen for open. So in order to get vulnerability disclosed to the GCC, what you actually do is you disclose it to people in Red Hat who also happen to work in their spare time on GCC. Therefore, they can see that the fixes are all teed up and ready to go once so it's actually quite a complex process, and it was very instructive to take a complex vulnerability through it, which could be fixed by being fixed at the language level or by being fixed in the editor or the front end of the repository. Another thing that really made a difference was validity. Once we finished the embargo period, we got headline coverage from Boucher and Brian Krebs, and various other pieces of technical press, and that was certainly useful in getting the stragglers to move on and actually show the patches that we were talking about. So with source code, there's a number of different things you can use. The code editors and repositories are one way, that something is wrong. Compilers can also throw error messages. In one case, there's something is done in a linter. And there are also other tools such as static analysis tools, which can point out that something is askew. So we have a reasonable grasp, I think, now of the Trojan source vulnerability. It's not entirely fixed. Some of the fixes aren't perfect, and you may always have a company that's trying to maintain Java code with an obscure editor that hasn't bothered to fix the vulnerability. In that case, I'm afraid you're a sitting duck. However, that isn't all that we learned from this exercise. Let me first show you how a number of the tools did it. GitHub's front end is something that's very widely used. And as you can see, this throws up an explicit warning here in a banner at the head of the page. And it also reveals the hidden characters by putting the Unicode code points with red boxes around them. On Rust, there is something similar. And in fact, if we look at GitLab and VS Code and GCC, there's a great range of error messages now which should point out to anybody who's not entirely asleep that the piece of code with the Trojan source exploit in it is something that should be looked at a little bit more carefully. So far, so good. But what about machine learning? Well, the obvious way to do a machine learning defense is to sanitize the inputs. There's other things you can try. Some machine learning people on our original team said, well, why can't we just OCR, why can't we just render the text and OCR it, because then everything gets done in the machine learning model? And yeah, you can do that, but it's a bother, it's a lot of work, it burns compute, and we've got ways of attacking that too. So the obvious way of doing a machine learning defense is to sanitize inputs. And here's the shocking thing, that although most of the languages and editors released fixes for the Trojan source vulnerability, either on disclosure day or within a couple of months of that, so far there's only one big NLP service that has done anything to mitigate the attack on their machine learning models, and that's Google. The other large suppliers of NLP models basically haven't done anything at all. So there's a big question, what's going on here? What's the difference between machine learning models and regular code, that we can fix regular code, but we can't fix machine learning models? Well, one of the things that you might wonder is maybe machine learning models are too expensive to update. We hear of the latest models costing $1 million worth of electricity and 6 months of machine time to train. And in that case, updating the model itself definitely is expensive, but you can sanitize the inputs easily enough. And so why isn't this done? Is it that the companies don't know that address sanitization is necessary? Well, if the vendors in question are IBM and Microsoft and Google, then they definitely do know that, because IBM and Microsoft were already trading at the time of the Morris worm. And Google, for goodness sake, puts enough effort into sanitizing inputs to its web forms so that they don't get hit by cross-site scripting vulnerabilities. So although the company itself may understand the need to sanitize inputs, perhaps the teams don't do this. And at one company where we spoke to people, we heard that the machine learning and security teams basically blamed each other. The NLP folks said, this isn't an NLP problem, it's a security problem. Stop being annoying, stop bothering me about this. And the security team said, you mean you're taking stuff off the internet and throwing it directly into your system without sanitizing it? How dumb is that? I mean, that's just so dumb, it's not really a security problem, it's an IQ problem. And so you end up getting a system of mutual blaming with no suitably senior vice president in a position to roll their sleeves up and start to make things happen. Now, we do know that security and safety are whole system properties, but who's responsible for which property of the whole system? Now, I should mention in passing that other machine learning teams also tend to ignore this, because we've done a bit of work recently on adversarial machine learning. For example, one of the authors on the bad characters paper, Ilya Shmailov, was sponsored by Boucher, who was worried about adversarial attacks on machine vision. And there, it's often very much simpler to do the input sanitization outside the machine learning model and then recover from attacks on your machine learning model using other mechanisms. In the case of a car, just sound the alarm and get the driver to take over would be one example. And that's a sensible way of dealing with very, very rare attacks, which would be very expensive to deal with if you dealt with them using a more complex model. So we are aware of the problems in general that the industry has with doing whole system security on systems that have got machine learning components and components built out of regular code. So here's my suggestions of topics for future work on the dependability, maintainability, robustness, resilience, etc., of systems built out of code versus systems built using machine learning models. Here are the sort of things that we should perhaps be collecting data on and studying. First, what's the cost of an upgrade or a bug fix? That could be extremely high if it's $1 million to retrain a model. It could be very low if you're doing software as a service development and you're committing tiny little upgrades and bug fixes to your product, several times a day. What's the time to do an upgrade or bug fix? Again, if you have to take 6 months to train a model, or if you have to wait a month before your next update to Windows, then that gives a significant amount of latency. Whereas again, with software as a service, you may be in a position to ship something on a basis of minutes to hours. Here's another thing that we should be looking at. What is the culture of C coders versus the culture of data scientists? Now, people who do ML are called different things in different companies, but data scientists tends to be the more common term nowadays, and it incorporates everybody from old-fashioned statistics professors to youngsters who play around with deep neural networks. So there's some diversity there. There certainly doesn't seem to be the ingrained culture of people who work on critical code and things like operating systems, where for at least 20 years now, it has just been how people operate, that you have got a security development lifecycle with vulnerability disclosure, with regularly shipped patches, and so on and so forth. Another issue, which may be at play here and may be separate, is the expectations of dependability. What do you expect of a system, and how do you measure it? Do you measure it in terms of the number of crashes reported to your servers per billion user days of your mobile phone operating system? If it's a piece of avionics, your expectation of dependability would be how many thousand hours mean time to failure. What is the expectation of dependability of machine learning models? How do we even reason about that? There's an awful lot of philosophers writing long-winded papers about explainability and ethics and so on of AI. But come on, guys, where are the metrics? Where are the numbers? What sort of numbers do you expect in which circumstance? Now, we already see in debates, for example, over upload filters, that there are widely varying claims made for the false positive rate and the false negative rate of, for example, detecting illegal images or subversive speech. But these tend to be tussle spaces. You know, they are things that people argue about rather than things that you can measure clearly with experiments that are repeatable by an outsider. Another issue is the publicity that you get for code bugs versus machine learning misbehavior. Now, everybody kind of expects that machine learning systems will misbehave a bit, and there's such an enormous literature nowadays on adversarial samples in machine learning, and so many people have written so many papers and tried to get press coverage in the technical press that people are kind of weary about it. However, code bugs are still newsworthy because new code bugs come along pretty well every week that result in real exploits, that result in real embarrassment for real firms, and which result in, for example, some new ransomware attack. So there's a publicity dynamic here as well. The next thing to explore and to think about is competition and its ugly stepsister, market power. Now, as I mentioned, we disclosed the Trojan source vulnerability to 19 different maintainers of languages or editors to begin with, and it got taken up by others after that. But the machine learning systems with which we experimented were only 3. So that gives you some feel for the fact that the market for NLP systems is already much more concentrated. And if you're someone like IBM or Google or Microsoft selling an NLP model to someone like Deloitte, who then sells to Facebook or Twitter a hate speech removal service, there are several links in the chain between the people who maintain the machine learning model and the moderators or other people at the sharp end are having to deal with all the hate speech and spam and abuse. And so the NLP suppliers are not only more powerful, they may also be more insulated. And finally, there's an issue of the maturity of the technology and of the market. If you're an extremely powerful player, then it's possible to ignore the market for quite some time. And through the 80s and the 90s, Microsoft basically ignored dependability issues, and everybody joked about the blue screen of death, and viruses got ever more prevalent. But eventually, in 2003, the complaints from other CEOs had become so vociferous that Bill Gates finally had to have his security jihad and get everybody at Microsoft who wrote code to go and do a course in writing secure code. So perhaps that is still in our future for machine learning. We can hope that it will happen given the concentration of the market, but the question is going to be when will it happen? Certainly the market cannot yet be described as mature, because people are coming out with all sorts of new stuff that gets described as machine learning, and sometimes may even include some machine learning components in it. So what are the takeaways from this talk? Well, the first thing is that Unicode makes it really easy to hide invisible vulnerabilities in source code. And the second thing is that it makes it really easy to break text-based machine learning. And the third thing is that defenses exist for both. And so the big question now is, why is the machine learning community not listening? And with that, we've come to the end of the slides, and it's time, I believe, for questions.
All right. So I think we've got a microphone up here. People online can hear. If there's any questions, please feel free.
Maybe I read it.
Yeah, how about I? Thank you.
So question from Greg Shannon. As you consider the CV entries, did you consider one or more CW?
Yeah, I can take that one. CWEs are interesting. So for those that aren't familiar with them, CWEs are common weakness enumeration one level above CVEs. Oftentimes a CVE will be described as sitting under a CWE or more than one in terms of the categories that describe it. That one is tough. So CWEs take a long time to produce. It's not something like a CVE where, frankly, if you want to go the certificate, the CNA, the naming authority of last resort, you basically send an email, and like 30 minutes later you have a CVE number listed for whatever it is that you do. If you are talking about having a process that involves a whole bunch of, presumably involves interfacing with groups like MITRE for extended periods of time. Now, it's actually worth noting that there is one CWE that is, I guess I would describe it as adjacent to kind of the Trojan source work. And I say adjacent because it's specifically focusing on domains and issues with domain spoofing. And when you go back, it seems like about 20 years ago was the time where everyone became really, really interested in, like, what does it mean to have two domains that look very similar, like the domains that you would type into a web browser. It was a classic attack a while back where PayPal.com was spoofed by someone actually using Ascii characters that did pay pi, like PAI instead of PAL, but it looked close enough to PayPal that it resulted in a pretty effective scam that caused some scammers to make all different money. And a whole bunch of discussions spun out from that, years of research and how we can improve domain security. And the bottom line is there actually is a CWE that says two strings look very similar to each other. And that, in my mind, it's something probably ought to be expanded together. This just caused a problem in general, not specific with domains, but those sort of conversations are not things that we feel like we could have within the context of, say, I believe we spent 99 days on our coordinated. Yeah, it's a really good point, and I hope that's something that results in the long term.
I would back that because 15 years ago we were also seeing internationalization and confusion attacks in like Postgres. for example. But I wanted to hear about your experience with the Unicode standard. If that's not going to like eat the
there's a lot in that. Like build people like that, or get them on conversations in practice, presumably be implemented into Unicode. What would they like to see? I don't know if I can say that's turned into anything particularly tangible yet. There's a bunch of proposal documents that are publicly available for review, and it's been really interesting to see that process develop. But I mean, at many there's a question of what does a change look like for Unicode, right? Because if you just a specification, manipulate something.
Sean, that would be
Good.
another
Okay.
meeting.
Okay. Fantastic. Yes. Ross, can you hear us now? No.
Yes, I can hear you. You dropped out for 3 or 4 minutes.
Okay. Ross, there was a question earlier about what sort of changes you would like to see to the Unicode specification. It talked for just a minute, but I'm curious if you have any to add.
Well, if you have characters in the Unicode specification that do dangerous things, then the specification should have an appropriate warning about them. It's probably not enough of itself, but it's useful to have it in the specification so that people like us can then go and speak to the guys in charge of the spec for Python or JavaScript or whatever and say, oi, you know, you're not standards compliant. That makes you liable. Your ass might get sued if something goes wrong. And that would give the developers the necessary leverage to go and say to their managers, we need some budget to go and fix this stuff. Right, like it or not, large corporates tend to be compliance focused when it comes to maintenance effort like this. Can you hear me, Nicholas?
Yeah. Yeah, there we go. There we go.
Okay, there we go. Ross.
Yes. Let me ask a follow-on question, Ross.
Sure, go for it.
There is a little bit of delay, but I'll repeat myself. It seems that we're dealing here with a neglected fundamental of distributed system engineering. Every interpreter, including humans and editors and every other agent, should in fact be demonstrably agreeing on the interpretation of any input.
No, that's
And
too
it
hard.
seems trivial.
No, come on, that's way too hard. You know, almost 150,000 Unicode characters. Nah, nobody's going to do that.
However, you would probably agree that there needs to be a principle that one needs to be able to point to in such cases. And this principle seems to be really simple, and as we just found out, it's not. And really fundamental, which we just found out is.
Well, there's a principle here, which is that any system acquires features until the feature interaction breaks security and safety. We've seen this in one area of research after another. Even the supposedly most secure things in the observable universe, the hardware security modules that banks use to hold their cryptographic keys to authenticate payments, by the 2000s had acquired so many transactions that if you got a bright grad student to stare at the manual for 2 weeks, he could say, aha, do transaction 147 and then transaction 63 and put the results of both of them through transaction 347, and out pops the master keys. This happens again and again and again. How do you stop it? How do you stop feature bloat? Well, if you're a company like Apple and you can have an absolutely dominant CEO who is obsessive about design, then maybe you can do it that way. But that has got very substantial costs for the whole ecosystem and for everybody else. You know, these are fundamental things around the economics of security and dependability, which probably placed long-term limits on lifetime of systems, ability to maintain stuff, and so on and so forth. This is fascinating stuff, but I think it's stuff that's studied at the workshop on the economics of information security rather than at LangSec. Weiss, by the way, is next month in Tulsa. If you want to come along, please do.
Yeah, maybe we can have a session on economics of LangSec. Sure, as it were, because your entire analysis of the response seems to be exactly in that ballpark. Maybe one last question, unless there are questions from the group.
There's one over there.
Oh, okay. Let me do you with the microphone.
So my question is with regards to the Unicode rendering. Did you come across any parser differentials with different editors when they were rendering these left to right or right to left Unicode fonts? Thank you.
Yeah. The question being, we see differences between editors in bidirectionality implementation. Yes, yes, absolutely. And that was one of the, it was both surprising and then stepped back to think about it for a minute and entirely unsurprising at the same time. So, you know, let's give some examples here. At first, when we were coming up with these Trojan source attack examples, we had some pretty complicated stuff that had dozens of different control characters nested within each other on a line to have a super fine-grained, you know, reordering of tokens. And it works fantastic in, let's say, VS Code, which is built using Electron, so it runs on Chromium, and Chromium, we believe, powers the bidirectional implementation. But then you take that and you copy it over into some other application that's perhaps more native, like Xcode or something like that. And all of a sudden it doesn't work because now you're using the operating system implementation of bidirectional as opposed to you know, what came from Chromium or from a web browser, and you paste it into some WebKit-based web browser, and it's totally different now. There were kind of two things that did for us. So one, it meant that either we had to stick to really simple examples, because if I just set something to right to left and then back to left to right, like that's going to be pretty much the same everywhere. The basic functionality doesn't cause a problem. But second was that if we were going to have really complex things where we have like dozens of different control characters, we had to go test them on a whole bunch of these different systems and then add in things that had an effect on one platform but didn't have an effect on the other platform in order to have this monster of a code that seemed to work on all of the different systems. So but what does that mean in practice? Unicode does publish a little bit of source code that handles some rendering and control character resolution things related to Unicode, but it's not a large code base, and I think many operating systems and large software products choose to implement it themselves. So yeah, what does that look like? I don't know, maybe we need some rigorous test set that everyone can agree on and have predictable results, but there's definitely differences in implementations.
I was just remarking in the chat there that one of the things that we struggled with when preparing these slides is that we've got that Arabic phrase, merhaba bil alam, on an early slide. And although that renders correctly on the standalone version of Microsoft PowerPoint, we were completely unable to figure out how to do it properly on the Office 365 version of PowerPoint, which we were using to work on the shared slides. And it absolutely insisted on being at the right-hand side of the phrase, which is completely wrong for right-to-left text. So here you've got this amazing situation that Microsoft, of all companies, a company that's been going for 40-odd years and has been selling Arabic language support for at least 25 of those years to millions and millions of customers in the Arab world, you know, not to mention other right-to-left places like Israel and Pakistan, cannot get you know, the rendering of right-to-left punctuation consistently correct in two instances of the same product. You know, that's an example of how hard it is to do design right once you have got enormously complex sprawling specifications and enormously complex sprawling products.
One follow-up question. I heard that for interacted with different programming language communities, and you've got positive responses from the Rust community and the Haskell community. They incorporated changes quickly, which implies that the ecosystem for akka, for theorem proving, would be fixed as well. And I'm wondering, what about COG?
Yeah, no, it's a good question. So yeah, did we reach out to the bureau? No, well, we did not reach out to them. So, and it was who do we reach out to in this situation? So we had a few different phases to our coordinated disclosure, and perhaps going into slight more depth than we did initially in the slide. So first, when we were just messing around and realized that there were some vulnerabilities here, we looked at C and a couple of other languages and said, okay, well, clearly there's some impact here, so let's reach out to the people who maintain these tools. And then, okay, we start putting a paper together and say, hey, we should be much more rigorous and test a whole bunch of different tools. So we test a whole bunch of others and say, okay, well, now since we know these are affected, let's reach out to everyone involved here. And that's where we step back and say, okay, so there's probably broader issue, and yeah, we can reach out to 19 different companies or something like that, but we can't guarantee that that's a comprehensive list. So at that point, we reached out to the CERT Coordination Center, which is a government partnership run with CMU, and that was very interesting because they definitely helped by adding in more affected software products than what we initially considered, but even then, it definitely wasn't comprehensive. And you provided an example of a language that we didn't reach out to, and I actually don't know what the story would be in that language about these attacks, and that is the case for the entire set of languages other than what we talked about in the paper. So yeah, I know that once we released the information, there were a lot of different GitHub issues that I saw pop up about this attack for languages that we hadn't previously considered, and some that made changes very quickly. But yeah, while I would have loved to have talked to every language team out there, I am unaware of a single place that I could put information that would get stuff to everyone who needs it. And that's actually perhaps an interesting tangent because, at least very briefly, there is a fantastic distribution list of operating system maintainers that you can reach out to when you have a vulnerability. And the intention is, patches should already be available. Reach out when the patches are ready, but before you go live with it, so that these OSs can have their updates ready to go. And this is particularly poignant for various flavors of Linux. But maybe the answer is that we need something like that for maintainers of languages, or if it exists already, then maybe I need to learn about it, but I haven't been able to find it. So.
In fact, I would say any data format.
Yeah. Fair. Yeah, it's not exclusively languages. There were some interesting conversations that developed, especially during the review process for this paper, about configuration files and what does it mean if I have some, I don't know, JSON or YAML file or something like that is doing critical task for software. Yeah, I know you've been really patient. Thank you.
From before your paper was published, Unicode had at least 2 technical reports published on security considerations and security mechanisms around Unicode. I will conjecture that by the time you're expecting, I've read these reports in the distant past, I will conjecture that by the time you expect developers to read tens of pages about security considerations for a character set, you have already lost.
You're right.
I mean, it's great work. The modern world has gotten so doggone complicated. And what do you do? Highlighting. Sam was asking an interesting question here about log files for having a little side chat. But I have the problem in my professional career. One of the reasons log4j was so problematic is I do not want to sanitize input to the logging routine.
Yeah.
I need to be able to log exactly what I got, and I need to be able to read exactly what I got. I mean, that's just like a very fundamental. So, I mean, it's for late here. So
Well, actually, maybe just add a couple of thoughts to that. So, I completely agree with you. the Unicode specification is huge, and like, to be fair, it's huge for a reason. Like, there's a lot of nuances to every language in the world. I mean, they have some ancient languages there that haven't been in use for thousands of years, that kind of stuff, right? Yeah, like what does that mean in practice? So my hope is that if we end up with changes to the Unicode specification, that we'll get like a little one-pager that comes out of it saying like, yes, there's these dozens or hundreds of pages that you can go read about the spec that probably someone has to read somewhere if they're building something from scratch. But if you're someone who maintains a code editor who's written in Electron on evenings and weekends, read these 3 paragraphs and it'll give you an idea of what's going on. And that's what I'm really hoping for. But then the other thing that gives me a little bit of hope is this particular attack, because it could be mitigated at so many different stages in the pipeline. I mean, yes, you can have a code editor that can surface something by syntax highlighting or potential encoding, highlighting, something like that. But you could do the same thing in a repository front end like GitHub's website. But you could also do the same thing in a compiler. Interpreters are a little bit weird because does this constitute a runtime bug? That's a hard conversation. But and then you've got static code analysis, which is perhaps, some may argue, even the most appropriate place for this, and not to mention language specs if programming languages spec changes. So like, because there's so many different places, I'm hopeful that at least like one entity in that pipeline pays attention. But yeah, it's an uphill battle. Ross, by all means, feel free to chime in, and we'll just mute here when you start talking.
No, it's better for you to handle questions because you don't have the round trip delay that I have.
Sounds good.
Do you think there are any legitimate use cases to nested directionality?
Yes, yeah. So question being, are there potential legitimate use cases for nested directionality? I think the answer is yes. And I think that it exists for a reason. Now, you could probably have some reasonable heuristics. Like if I have 20 layers deep of like nested bidirectional isolates inside a pretty short string that otherwise contains only ASCII characters, like, yeah, I'd be pretty confident that's malicious. Yeah, I mean, you can imagine speakers or writers of languages, even just 2 languages that have differing directionalities, and when they try and interweave text from those different languages, quoting one inside to the other or things like this, oftentimes word processors, operating systems will add in.
That's exactly the difficult case, because about 40 years ago, I was working on some typesetting equipment that did do bidirectional stuff. So you could typeset Arabic and English or Hebrew and Russian or whatever in the same page. And if you were trying to typeset an English quote in an Arabic newspaper, for example, it was pretty much a nightmare because you ended up having to worry about justification of text, making the text align with the edges of the columns, where you would have something going right to left and then something going left to right, and then you'd have to juggle it to the right and then pick up right to left afterwards. So it's for that the bidirectional control characters basically had to be invented. However, you're right in that a limited amount of nesting should be sufficient for such purposes, or you should insist that people use some pseudo or escape sequence to do it. Or alternatively, as we learned, in fact, from interacting with the Rust team, that it is sufficient to stop these attacks on source code if you simply cry foul whenever there's an unterminated BD sequence appearing anywhere. And if you see that anywhere, you might as well just drop that whole source code file on the floor and sound the alarm. So once you start looking at the detail, there's various things you can do.
And I might just add as a thought experiment that was interesting to me, how quickly you can enter into the realm of high complexity for kind of bidirectional issues. So like, imagine someone who's writing a source code file who is bilingual in, let's say, I don't know, Arabic and Russian or something like that. All of a sudden, you have source code which looks a lot like English in a lot of cases, and then maybe they have a comment that starts in Arabic. Well, now you've switched directions, but then inside that they quote something that's in Russian, and now they use Arabic numerals to describe. It's just like it goes on, and then you've got punctuation, and how do you make sure the punctuation's on the right side of the characters, and all of a sudden, whether that user is used to pressing the special keys to get those control characters in there, or whether the OS just dumps it in for them, or the code editor. And actually, there's one other small interesting point. There was an attack quite a long time ago. It's a really fascinating attack. I want to say this was in the like 17, 18 years ago range, where someone found that on certain versions of Windows, you could put right to left control characters in file names and to make it look like the file extension was different than what it actually was. And that worked really well with like email attachments and drive-by downloads, things like this. So in response to that, it seems that some pieces of software started putting left to right kind of control characters inside things that looked like file names all the time to prevent that from happening. And artifacts of that are still floating around GitHub and other code bases all the time. So like there's a whole mess underneath all of this.
And we haven't started talking about homoglyphs. Dropping the example we had then was the Cyrillic N in place of the English H. But there are many, many others, and there, I mean, if you read our papers, you see there are some cases where these can be leveraged into attacks, even on source code. They're much more common as attacks on natural language processing systems, and some of these are actually seen occasionally in the wild. We have a colleague, for example, who might interweave Cyrillic and English characters in order to stop something being automatically translated. And some people find that useful. Now, again, you start getting a whole bunch of rules for your input filter. You might decide that you're simply going to alarm at and discard any piece of text that mixes characters from two different languages in the same word. You can have a word can be all Cyrillic and or all English, but not a mix. But again, you would probably find some weird edge cases where that discombobulated a regular user. And again, how do you go about rolling this out at scale? I suspect the big NLP firms would really rather not have to sit down and think about this because it would be complex and you'd be risking all sorts of unpleasant side effects. But it's inevitable that it will eventually have to be done.
It may be worth saying as well, one of the common responses that I saw a lot of language maintainers talking about is, well, gosh, if we put out, say, a compiler error that comes from things that look like unterminated bidirectional control characters in source code, like we're going to end up breaking a ton of legacy code, and worse, we're going to do it in like very specific regions in the world where we're more likely to encounter these characters, and that just feels like something we really don't want to do. So it's hard problem.
Well, they were probably wrong, because when we went through all the GitHub stuff, we didn't find a single case of an unterminated BD character. So, I mean, that could have been universally deployed.
I think we found unterminated not in malicious environments.
Oh, okay. I stand corrected then.
In Keynote, function differentials are absolutely everywhere, right?
Thanks.
We will have a short 10-minute break at this point, and thank you again.
Thank you very much.
Thank you.
So, announcement.